Hello everyone, welcome back to another video. Today we're going to be discussing undamped mass spring systems. So from its name, it has two parts, a massless spring with a spring constant K and a mass with mass M. And when we say the system is undamped, it means that there is no air resistance or friction. We can neglect it, or we assume that it's zero so that its natural frequency is not going to be affected. It's not going to decrease. So by Newton's first law, it is going to go forever and ever. It's going to oscillate back and forth, and to have it's not going to have a change in natural frequency. So when we attach mass m, obviously it's going to cause a downward motion in the spring. However, it's going to have a reaction force. It's going to have a restoring force caused by the spring, and it's going to go up. And in an undamped mass spring system, it's going to go on back and forth, back and forth, back and forth, and it's not going to stop. So how are we going to model this equation of motion? So from our lower physics classes, we know that in a spring system, the equation of motion is sinusoidal. So how did we arrive to that? So apparently, the equation of motion of a spring mass system can be modeled using a second order linear differential equation. So how did we go there? So I'm going to show you the derivation. So consider this mass spring system with spring constant K and mass M. Let's do the FBD. Obviously, the weight is going to pull it down, and it's going to have a restoring force causing the mass or the system to go up. So we know that from Hooke's law, F is equal to Kx. So let's move these arrows around and let's stretch the spring by a distance L. So that distance L is caused by the initial weight of our mass. So when the system is at equilibrium, meaning it's not moving, the mass or the weight of the system is going to be equal to K and the distance that it was displaced, L. And let's stretch it even more. So let's say that you were the one that stretched it. You pulled it and you're holding it so that it does not start the oscillating motion. Let's call that distance L and plus some distance x. So by Newton's second law, we can derive this equation of motion by equating F is equal to ma. So these are the sum of forces and equated by the direction of acceleration, which is going to be upwards, because when you pull the object and you release it, obviously it's going to go up. So equating these two, it says mx double dash is equal to mg minus k times x plus l. So where did the x double dash come from? Recall that the second derivative of position with respect to time is equal to acceleration. So what we did is we just replaced it with x. We replaced the a with x double dash. So we have our working equation here. We can simplify this even further by distributing the k. It's going to be negative kx and negative kl. But recall, L is the distance of equilibrium, and therefore at equilibrium, KL is equal to mg. So what's going to happen is just going to cancel out. KL and mg is going to cancel out, and we're going to be left with mx double dash is equal to negative kx. Putting that in the other side of the equation, we have this, a working equation, our working differential equation that we're going to use. Solve sample problem number 1. Consider the undamped spring mass system with a ball weighing 39.24 newtons, causing the spring to be stretched by 0.61 meters. Using Laplace transform, find out how much the spring stretches when the system starts out at time is equal to 0. At its equilibrium position, x is equal to 0, with a velocity of negative 10 meters per second. So this makes sense of what we're given. Let's put it here. Our weight is equal to 39 newtons. Our initial length, or our length at equilibrium, is equal to 0.61 meters, and we're going to assume that that's going to be our point of point of equilibrium. So therefore, at that point, x is equal to 0, and our first derivative is equal to negative 10. The first derivative is our velocity, and what does a negative mean? What does a negative velocity mean? It means that we have pushed the mass upward, so the spring is going to be compressed rather than stretched. So when we release it, it's going to do a downward motion. So what we're trying to find is how much the string stretches, and we're not going to find that without the position equation or the equation of motion, I mean, and that's what we're going to find. So let's draw the FBD first. And the first step in our solution is find the differential equation. So this is our working equation. And right, we don't have mass is not given, only weight and also k. K is not given, so we're going to solve that individually. That's very easy. Just substitute the formula for weight divided by the acceleration due to gravity, and that's our mass. As with the spring constant K. Just consider the equilibrium position of the spring mass system, mg is equal to KL, and substitute. And that is our spring constant. And substituting these values into equation 1, we have this. This is our working equation. That's what we're going to use to solve for the position to the equation, for the position function. Step 2 is to solve the DE. You can use other methods, but we're going to use the Laplace transform because it's easier. So this is our differential equation, and this is our conditions. Again, at equilibrium position, we're going to assume that x is equal to 0, and our initial velocity is equal to -10. So recall the Laplace transform of derivatives. Here it is. Here it is. We're going to do is we're going to substitute this to this and substitute this to this. So getting the Laplace transform, I highlighted it. So this is the x double dash. I just put this here and attach the constant 4 plus this. I just replaced x with x of s times the constant 64. So distributing 4 yes as this. Obviously, if we put 10 here, we're going to get a positive value. Times 4 is equal to 40. Our initial displacement is 0, therefore this will equal to 0. So factoring out x of s, we get this. And solving for x of s, we can finally be able to solve for the differential equation using reverse Laplace. So here's our working equation. So what we can do first is take the 4 out, since 64 is divisible by 4, gets us this. And recall that the reverse Laplace of this function is equal to sine k of t. So with the equation we have here, malapit na. Ang kailangan, may s squared na tayo, tapos may k squared na rin tayo, which is yung 4. So ang gagawin na lang natin, yung 40, gagawin natin k or 4. Madali na lang yun dahil divisible naman by 4 yung 40. So labas na lang natin. Factor out natin yung 40, magiging ito. So lalabas natin to, -10 and 4. Simplify. And ito na mangyayari. Ito, 5 over 2 times 4 over s squared plus 4 squared. So pwede na natin ito i-Laplace, no? Pwede natin ito i-Laplace. And ang ating magiging final answer ay ito. Tapos natin ang Laplace transform. So obviously 2.5 ginawa ko lang numerical, ginawa ko lang decimal. Tapos yung 40, yung k. Ito, k, which is yung 4. So ang hinahanap sa atin is yung how much the spring stretches. So obviously, kung inanalyze natin yung function na to, malalaman natin yung amplitude, which is yung katabi lang to ng sine, which is 2.5. Yun ang magiging maximum stretch ng ating spring. So therefore, ng ating sagot, x is equal to 2.5. So ito na. Madali lang siya. Madali lang siya. Ito na ang ating sagot sa ating equation, and hopefully, naintindihan nyo ang aking pag-explain. Ito ang aking sources. Kalagay ko na lang ang PowerPoint sa description para tingnan nyo na lang sa sarili nyo, pag-aralan nyo. And yeah, thank you guys for watching. Bye-bye.